Okay, in this video we are looking at covalent networks, which we look at as a lattice, and their properties. We're particularly focusing on carbon networks because there's so many different varieties of carbon allotropes. So we're going to talk about the different types of carbon. So the first one to look at is the most famous form of carbon, or definitely one of the most expensive, is diamond. So diamond is what we call an allotrope of carbon, and allotrope is a form of an element. It's a form of an element, okay, and it depends on the element's structure. So because carbon's got so many possibilities with its structure, it forms different allotropes. So diamond in particular is interesting because the network is all entwined, so you've got tetrahedral geometry. So if we look here at the tetrahedral geometry, you can see here every carbon is bonded to 4 other carbons. And that means that it's actually a very strong structure, very hard structure, very difficult to scratch, which gives diamond some interesting material uses. And it's also very high melting point because there are many strong covalent bonds. And that means that in order to melt something like diamond, it takes thousands and thousands of degrees to do it because you're breaking so many and such strong bonds. The reason it's so hard is because if, for example, the edge of a diamond crystal, say the top of this here, is brought into contact with another material, the force that is kind of put on that particular atom is distributed down to its network like this, okay, and then that force is spread out even more as the sort of force dissipates almost throughout the network. So that gives rise to its hardness. So depending which end of the crystal is touching another object, that atom is strengthened by its neighbouring atoms' bonds. So we actually use diamonds to as a material for cutting tools, so saw tips, saw blades, and drill tips. Sorry, and we also use it to test other materials' hardness because diamond can't be scratched. It's used to scratch or dent other materials to see how big the dent is on those other materials. So that brings me on to the hardness scale in a moment. The last material we're going to look at in this first bit here is silicon dioxide, which is sometimes called quartz, okay, and it's a crystal commonly found in lots of mineral rocks. And this is also a tetrahedral structure, but this time with 2 different elements in there. So you can see here how every silicon is bonded to 4 oxygens, and then each oxygen is bonded to 2 silicons. So that creates a tetrahedron, which you can see in the sort of crystal angles here, the way it forms. Obviously, these crystals, the slower that they have, that they form deep underground, the bigger the crystals can grow. And they actually, if they grow slowly enough, they can present structures which actually resemble the lattice structure quite markedly. So we're talking about hardness. Hardness is rated on a scale of 1 to 10. And at the top here you can see diamond. Because diamond is the hardest material, it's used as the kind of benchmark material. Like this is the hardest one. And they use a sort of hammer test. Well, this is one of the tests. They use a hammer test and they measure the size of the dent from a diamond hammer into another material, and that gives a rating of how hard these materials are. So you can see some familiar substances in there. Talc at the bottom here, that's the stuff that used to be in baby powder. We've got quartz crystal. Fluorite is another hard mineral that you can get, and you can see the uses that you've got for them. So you've got like drill bits, etc. at the top there. So that's a sort of a common property with these covalent lattices. So looking at other properties now of covalent lattices, so we've talked about hardness, and that's particularly notable. It's also got high melting point and boiling point. So all of these things are similar to ionics. But then we've got some differences here. So non-conductor of electricity both as a solid and a liquid. Well, the liquid part for certain is different to ionics, because as we remember from previous classes, ionic substances, when they're melted, when they're molten, they are able to conduct. They're actually a superconductor because they can carry charge, whereas this cannot carry charge because there is no charge. Okay, so in an ionic substance, you've got negative and positive ions. In this substance here, we simply have covalently bonded atoms, so there is no charge to be carried. Similar to ionics, we have brittleness, and the reason for that is because it disrupts the lattice if we are to break apart the atoms there. Disrupts the lattice. So if we have a lattice of carbon here, okay, and we break the bond, it's very difficult to get that bond back together in exactly the same location that it was to start with. So that's why we say it disrupts the lattice. And that means that even though it's so strong to begin with, it actually, if it's broken in the right way, like when they cut diamond into their gem shapes, that's it. It's probably, well, it will be broken until it, the only way of reforming that would be to melt it again and reform it slowly as a crystal, which obviously for diamond is very difficult. Then we get on to chemically inert. So chemically inert is a common property here because the atoms are locked into place. They're locked into place, and so they can't react. Okay. Now this differs a little bit from ionics, but it depends on the ionic substance. But generally, covalent substances are much less chemically reactive. Lastly, insoluble in water. So this one is definitely different from ionics. Okay, ionic substances love water. Most of them are soluble in water, whereas this is not. Okay, and other solvents, being organic solvents, things like acetone. Again, this is different from smaller covalent molecules. So small covalent molecules often are soluble in either water or in organic solvents, other solvents, whereas this one is not. So because of the giant structure, they are all held together and they do not break apart to dissolve. Okay, so that's going through the basics of covalent lattices. If we now look at some specific examples in carbon allotropes, we've got graphite. So graphite is the most common allotrope of carbon. If it forms in a sort of crystalline structure, so underground or whatever, for a long time, it can form layers, and these layers are actually visible. Okay, so it's a layered structure, and if we look at the atoms, you can see that what happens is, rather than every carbon bonding to 4 other carbons, every carbon is bonded to 3 other carbons. Okay, and that means that if every carbon has a valence shell with 4 electrons in it, that means that there is a 3rd electron not involved in bonding. And this means that it is delocalized. And delocalized means it's not attached to any one atom. It actually sits in the middle. Delocalized electron. Now this isn't enough to create a actual covalent bond, but what it is enough to do is create dispersion forces, which you've looked at in chapter 7. So those dispersion forces keep the layers together. Each of these layers is called graphene. Okay, that's called a graphene layer. And the whole structure together is called graphite. Okay, the whole thing together. Now this layer structure gives some very interesting properties. So first of all, it's hard, just like its other covalent lattices. It's also very heat resistant. It sublimes, so that means goes from solid to straight to gas with no in-between stage at 3,600 degrees C. But this one's interesting. It is an electrical conductor because of the delocalized electron. And that can carry charge. So unlike other covalent lattices, this one is able to carry charge around from left to right, right to left, so positive to negative. Lastly, this is another common use, is as a lubricant for machines. So it's a dry lubricant as opposed to like oil, which would be a wet lubricant. And this is able to create low friction between pieces of metal, and that means that it's really good for big machines, but also things like door locks and smaller mechanical devices as well. So the reason it can work as a lubricant is because the graphene layers are able to slide over each other. And this is a key ability that it has, and that means that because they can slide over each other, they're not held exactly in place, and it means that they can move apart and help the objects in the machine actually move with them. So that creates a lubrication that is quite common in a lot of different uses. Lastly, we've got the other variations of allotropes. So for carbon, that is. So we've talked about graphene already. There's also amorphous carbon. That's something like coal, okay, or charcoal, and that's where it's formed probably a lot quicker through combustion. And coal is obviously made through fossilization, actually, underground. So that takes a long time, but it's a sort of a mixed structure that you get there. Then there's also what they call buckyballs. Now, a buckyball, or actually properly known as a fullerene, is a spherical structure where the carbons are all linked together in a sort of ball shape. Now, initially this was discovered in Australia, in Canberra, and they didn't really have any uses for it, but now they've found that there's potential uses in photovoltaic cells, so solar power. Lastly, the most important one are the nanotubes. So nanotubes are layers of graphene which are wrapped around and turned into a tube. Now these tubes vary in size and in the kind of arrangement of where the hexagons lie, but they have the ability they have the delocalized electron, so they conduct electricity, which is really useful. So the other thing that they are able to do is they are very strong. They have high tensile strength. And this high tensile strength is what makes it useful for various engineering applications in the future. We haven't actually used it yet, but potential uses in the future. That's the end of looking through covalent networks. So now complete the chapter 8 questions.